Right now, a cloud of charged plasma the size of several planets is racing toward Earth, and it will arrive tomorrow. The US government has issued a strong geomagnetic storm watch, a G3. Most of the coverage you will see treats this as a light show, a gallery of pretty auroras over a lake somewhere. But that is the polite version of what this energy does, because a geomagnetic storm does not just paint the sky. It reaches down. It pushes electric currents through the ground, through the oceans, through the rock itself. And the question almost nobody will ask out loud is what happens when that energy meets a planet that is already, right now, shaking and erupting beneath our feet. Stay with me, and you will understand exactly what is coming. If you have made it this far, subscribe to the Quiet Archivist, because this storm is still unfolding, and the next pulse from the sun is already on its way. Drop a comment telling me where you are watching from, and whether the ground has been restless near you lately. Now, let's get into it. Right now, as you watch this, a cloud of charged particles, roughly the size of several planets, is racing across 93 million miles of empty space, and it is aimed at the part of the solar system where you happen to be standing. It left the sun on June 6th, and the people whose entire job is to watch for this kind of thing have already drawn the line on the calendar. Tomorrow, June 8th, 2026. That is when it arrives, and the United States government's Space Weather Prediction Center has done something it does not do lightly. It has issued a formal storm watch, and it has put a number on it. G3. Strong. I want you to sit with that for a second, because we throw around words like solar storm so casually now that they have started to lose their weight. So let me make it concrete. A geomagnetic storm is not a metaphor. It is not a vibe. It is a measurable, physical event in which the magnetic field of the entire planet you live on begins to shake. Not gently. The needle on a magnetometer that would normally drift lazily across the page starts to lurch. Compasses wander. Currents that have no business existing begin to flow through the ground, through the oceans, through pipelines, through the power grid that keeps the lights on in your house. And the engine driving all of it is a single eruption from the surface of a star. Here is what we actually know. On June 6th, at 1 minute past 2 in the afternoon, Universal Time, an active region on the sun, designated 4461, let go with a flare. As flares go, it was a modest one, classified M1.8, which is the lower end of the medium category. But the flare itself was never the point. What mattered was what came with it. The eruption launched a partial halo coronal mass ejection, a vast bubble of magnetized plasma blown off the sun's outer atmosphere, and it threw out a shockwave so fast that ground stations picked up its radio signature screaming across the spectrum at around 838 kilometers per second. There was an 11-degree long filament of solar material that lifted off the surface at the same time. And the coronagraphs, the instruments that block out the sun's blinding disk so we can see the faint corona around it, watch that bubble expand outward and begin its journey. That journey takes about 2 days, and the math, run by the forecasters at NOAA, lands the arrival squarely on June 8th, around the middle of the day. So what does G3 actually mean for you? The storm scale runs from G1, minor, up to G5, extreme. G3 sits comfortably in the strong category, the third rung of 5. At G3 levels, the aurora, the northern lights, can be pushed down out of the Arctic and become visible across the northern tier of the United States, sometimes as far south as Oregon, Illinois, even parts of the mid-Atlantic if the timing is right and your sky is dark. Power grid operators get notified because the storm can induce voltage irregularities in long transmission lines. Satellite operators pay attention because the upper atmosphere swells and drags on spacecraft in low orbit. High-frequency radio, the kind that aircraft on transoceanic routes still rely on, can fade out. GPS accuracy can degrade. None of that is the end of the world. We have lived through G3 storms before, many times, but it is real, it is physical, and it is coming. The forecast itself reads like a countdown. Through the daylight hours of June 8th, the planet stays quiet, the calm before the shock. Then, around midday, the leading edge hits. The disturbance index they call KP, which measures how violently the magnetic field is being shaken on a scale from 0 to 9, begins to climb. By midday, it crosses into G1 territory. A few hours later, G2. And then, in the window centered around 6 in the evening Universal Time, it peaks. KP7. Solid G3. The storm then holds at G2 strength deep into the following day before it finally begins to fade. That is the headline. A strong solar storm hits Earth tomorrow. And if that were the whole story, it would already be worth your time. But it is not the whole story. Because here is the thing almost nobody covering this storm will tell you. The aurora is the pretty part. The part you can photograph. The part that ends up on the morning news as a feel-good gallery of green skies over a lake somewhere. The aurora is what this energy does when it is polite. The question I actually want to chase in this video is what this energy does when it goes somewhere else. Down, into the rock, into the faults, into the magma. Because that is where this stops being a light show and starts being something that real scientists argue about behind closed doors, and have for decades. And as it happens, the ground beneath us has been anything but quiet this week. Hold on to that, because we are going to come back to it. To understand the question I just asked you, you have to throw out the picture most people carry in their heads. When people imagine a solar storm, they imagine something happening up there, in the sky, in space, a pretty curtain of light hanging over the horizon, safely overhead, while the solid Earth sits underneath it, untouched and indifferent. That picture is wrong. Or rather, it is only the top half of a picture that goes much, much deeper than the sky. Let me give you the real mechanism, and I am going to do it without the jargon, because the jargon is where most explanations lose people. Earth has a magnetic field. You know this. It is why a compass points north. That field is not a static thing, like a bar magnet sitting on a shelf. It is a living, breathing shield. And when a coronal mass ejection slams into it, the whole shield gets compressed and rattled. Picture flicking the edge of a soap bubble and watching the surface ripple. That rippling, that rapid change in the magnetic field over time, is the thing physicists actually measure during a storm. They have a name for it, and the name tells you everything. They call it dB/dt, the rate of change of the magnetic field, how fast it is shaking. Now here's the piece of physics that turns a sky show into an Earth event. There is a law, discovered by Michael Faraday almost 200 years ago, that says a changing magnetic field creates an electric current in any conductor sitting inside it. Any conductor. A wire, a metal pipe, a power line, salt water, and crucially, the ground itself, which is full of conductive rock and groundwater and mineral veins. So when the planet's magnetic field starts shaking during a storm, it does not just make lights in the sky. It reaches down and induces electric currents in the body of the Earth. We even have a name for them: geomagnetically induced currents. They are real. We measure them. They are the same currents that have, in the worst storms, melted transformers and blacked out entire cities. In 1989, a geomagnetic storm collapsed the power grid across the entire province of Quebec in 90 seconds. 6 million people lost electricity, not because something hit a power line, but because the shaking magnetic field reached into the wires and the ground and pushed a current through them that was never supposed to be there. Think about what that means. The energy of a solar storm does not stay politely in the upper atmosphere. It couples into the planet. It flows through the crust. And the crust, remember, is not just dead rock. It is a stressed, loaded, fractured system holding back the pressure of continents grinding against each other. Let me make that 1989 event even more vivid, because it is the single best proof that space weather is not a sky phenomenon. The storm that hit Quebec was driven by a coronal mass ejection, not unlike the one heading our way now. When it struck, the shaking of Earth's magnetic field induced currents in the long transmission lines of the Hydro-Quebec grid, lines that stretch for hundreds of miles across ancient, electrically resistant rock, which is exactly the kind of geology that forces those induced currents to find a path through the wires instead. Protective relays, sensing something deeply wrong, tripped one after another in a cascade that took the entire grid down in under 100.5 seconds. People went to bed in a province plunged into a January darkness, and the culprit was a magnetic field, 93 million miles from its source, reaching down and pushing electricity through metal that was never connected to it. If a storm can do that to a power grid, the obvious next question is what it is doing to everything else conductive that it touches. The pipelines, the railways, the seawater, and the rock. There is one more layer to this, and it is the one the source material I am working from leans on heavily. So let me explain it properly. Earth is wrapped in something called the global electric circuit. This is not science fiction. It is textbook atmospheric physics. Between the ground under your feet and the ionosphere, that electrified layer about 60 miles up, there is a standing voltage difference of somewhere around 250 to 300,000 volts. 250,000 volts, hanging in the air above you, all the time. It is maintained mostly by thunderstorms, which act like millions of little batteries pumping charge upward. And everywhere it is not storming, a faint fair weather current trickles back down through the atmosphere to complete the loop. You are, at this very moment, standing inside an enormous, planet-sized electrical circuit. Now drive a geomagnetic storm into that circuit. You are pumping energy into a system that is already wired from the sky to the ground. The ionosphere gets energized and distorted. The currents flowing through it surge, and the whole delicate electrical balance between the high atmosphere and the surface gets perturbed in ways we can measure, but cannot fully predict. So when someone tells you a solar storm is energizing the entire planet, they are not, in the loosest sense, wrong. The energy is real. The currents are real. The coupling from space all the way down into the ground is real, and it is documented. The question, the one that has divided geophysicists for half a century, is not whether this energy reaches the Earth. It does. The question is whether it can ever do anything down there that matters. Whether a current induced in the crust, a perturbation in the global circuit, a few hours of a violently shaking magnetic field can reach into a fault that is already strained to its breaking point, or a magma chamber that is already close to bursting, and become the thing that tips it over. And to answer that honestly, we have to talk about the question scientists really do not like to be asked in public. Ask a working seismologist, on the record, whether solar storms cause earthquakes, and watch what happens to their face. Because it is a loaded question, and they know it, and they have learned to be careful. The honest answer is more interesting than either a flat yes or a flat no, and getting to it requires one distinction that almost every viral version of this idea gets wrong: the difference between causing something and triggering it. Let me draw that line as sharply as I can, because everything downstream depends on it. Causing an earthquake means supplying the energy for it, and here is the wall that every solar earthquake theory runs straight into. The amount of energy stored in a major fault, The elastic strain that has been building for centuries as two plates lean against each other is staggering. A great earthquake releases more energy in a few seconds than a large nuclear arsenal. The geomagnetically induced currents from even a severe storm, the energy that actually makes it down into the crust, is smaller than that by an almost comical margin. We are not talking about a close call. We are talking about many, many orders of magnitude. The storm simply does not carry the energy of an earthquake. It cannot. It is like asking whether a sneeze can knock down a building. The building is already holding up tons of weight. Your sneeze is not in the conversation. So if anyone tells you a solar storm caused a magnitude 7, the physics says no, and it says no loudly. But, and this is where it gets genuinely interesting, triggering is a completely different idea. Triggering does not mean supplying the energy. It means supplying the final nudge to a system that already had all the energy it needed and was sitting right at the edge of release. Now picture that building again, except this time it is a boulder balanced on the very lip of a cliff, 10,000 years of geology having pushed it to the exact point of tipping. It does not take much to send it over. A gust of wind, a footstep, a vibration. The energy of the fall was already there, stored in the boulder's position. The trigger just chose the moment. And here is the part that should make you sit up, because it is not speculation. We know triggering is real. We have proof. The clearest example is the tides. The same gravitational pull from the moon and sun that lifts the oceans also flexes the solid rock of the earth, very slightly, twice a day. And on certain faults that are already critically stressed, seismologists have measured a real, statistically detectable increase in small earthquakes timed to the tidal stress. The tides do not cause those earthquakes. The strain was already there, but they appear to influence the timing of release on a fault that was already ready. We have also documented something called dynamic triggering, where the seismic waves rolling out from one large earthquake travel thousands of miles and set off small quakes on distant faults as they pass through. Again, not causing. The energy in those distant faults was already loaded. The passing wave was just the nudge, so the door is not closed. Tiny external forces demonstrably can influence the timing of an earthquake that was already going to happen. The boulder really can be tipped by a breeze. And that reframes our entire question. We are no longer asking the absurd thing, whether a solar storm can power an earthquake. We are asking a much more reasonable thing. On a fault that is already at its absolute breaking point, can the currents and the magnetic shaking from a geomagnetic storm act as one of those nudges? Can the energization of the global electric circuit be the gust of wind for a boulder that was already going over? Let me push the boulder analogy one step further, because the timing piece is where this gets subtle, and most people skip right over it. Imagine 10,000 boulders, scattered along 10,000 cliffs around the world, each one at a slightly different stage of being pushed toward its edge. Almost all of them are nowhere near tipping. They could sit through 1,000 storms and never move. But at any given moment, a tiny handful might be sitting right at the knife's edge, where the very next nudge of any kind sends them over. A trigger, if it works at all, does not reach out and find a random stable boulder and knock it down. It can only matter for the rare one that was already a heartbeat from falling. And that is the deep reason this effect, if it exists, would be so maddeningly hard to detect. Most of the time, a storm arrives, and there is simply no boulder near the edge for it to push, so nothing happens, and the storm looks irrelevant. Once in a great while, a storm might arrive at the exact moment a fault was already in its final hours, and tip it, and produce an earthquake that was going to happen anyway, just slightly sooner. From the outside, those two cases are nearly impossible to tell apart from pure coincidence. The signal, if there is one, is buried under an avalanche of noise. That is not a reason to dismiss the question. It is the reason the question has stayed unanswered for so long. That is a real scientific question. Real researchers study it. It has not been settled. And the honest state of the evidence is messier and more fascinating than either the believers or the debunkers will tell you. Because while the energy budget slams the door on causation, it leaves that triggering door open just a crack. And for decades, people with instruments have been trying to figure out whether anything actually walks through it. So let us look at what they have actually found, because the real research does not say what the headlines say it says. If you go looking, and I mean really looking, in the peer-reviewed scientific literature, not on a forum, not in a comment section, but in the actual journals where geophysicists publish, you will find something that surprises most people. The solar earthquake connection is not a fringe idea that no serious scientist will touch. There are real, published, peer-reviewed studies that report statistical correlations between solar activity and global seismicity. They exist. You can read them. Some of them appear in respectable journals. They take large catalogs of earthquakes, line them up against decades of solar wind data and geomagnetic indices, and run the statistics. And a few of them come back and say, there is a weak but detectable association. The global earthquake rate in some of these analyses ticks very slightly upward during periods of heightened solar activity. Now, before anyone takes a victory lap, let me tell you what that actually means, because the word weak is doing an enormous amount of work in that sentence. These correlations are small. They are contested. Other researchers take the same data, adjust the method, and the signal shrinks or disappears. The effect, where it shows up at all, is the kind of faint statistical whisper that could be a real physical phenomenon, or could be an artifact of how you sliced the data. This is not a smoking gun. It is a wisp of smoke that some people see and others insist is just a trick of the light. And in science, a result that one team finds and another cannot reproduce is not a discovery. It is a question mark. But there is a second body of research here, and this one stands on much firmer ground, and it is the one I find genuinely compelling. So pay attention to the direction it points. It is the study of earthquake precursors, electromagnetic precursors specifically. The idea is not that space weather reaches down and shakes a fault. The idea is the reverse. The idea is that a fault, in the days and weeks before it ruptures, while the rock is being squeezed toward failure, generates its own electrical and magnetic signals that we can detect. And the proposed mechanisms for that are solid physics. When you put enormous stress on certain kinds of rock, it produces an electric charge directly. That is the piezoelectric effect, the same principle that makes the spark in a barbecue lighter when you squeeze the crystal. As the rock microfractures under strain, it releases charge carriers. The stressed ground can push radon gas up to the surface, and that radon ionizes the air above the fault, changing its electrical properties. So, a fault approaching failure may, quite literally, light up electromagnetically before it breaks. There is a real and growing field built on exactly this idea, and it has a track record worth knowing about. Researchers using satellites have reported disturbances in the ionosphere, the electrified upper atmosphere, in the days before some major earthquakes, disturbances that appear over the region that is about to rupture rather than scattered randomly. The total electron content of the ionosphere, a quantity navigation satellites measure constantly, has shown anomalies ahead of certain large quakes. There are dedicated spacecraft that have flown specifically to hunt for these pre-seismic electromagnetic signals from orbit, and the proposed chain of cause and effect runs entirely upward. Stressed rock at depth generates electric charge and currents. Those currents and the gases they drive to the surface alter the conductivity of the air and the lower ionosphere directly above the strained ground. And that altered patch of ionosphere shows up in the data. The earthquake announces itself, faintly, by changing the sky above it. That is a coherent physical story, and it is being actively tested with real instruments. And it is worlds away from the cartoon version, where a solar flare reaches down and snaps a fault like a twig. Do you see why that direction matters so much? The well-supported science is about the Earth talking to the sky, not the sky talking to the Earth. Stressed rock generating signals that climb up into the atmosphere and even disturb the ionosphere overhead. That is a far better evidenced idea than a solar storm reaching down to pull a trigger. And the two ideas get tangled together constantly in popular coverage, because both of them involve electricity and earthquakes and the boundary between the ground and the sky. But they are pointing in opposite directions, and only one of them is on firm footing. So where does that leave the honest verdict? Right about here. The mainstream scientific consensus is that there is no established, mechanistically proven way that a geomagnetic storm triggers earthquakes or eruptions. The correlations that have been published are weak, fought over, and not reliably reproducible. The energy budget makes causation impossible, and the only surviving version of the idea, the marginal trigger on an already critical fault, remains unproven for geomagnetic storms specifically, even though we know triggering by other small forces, like the tides, is real. Meanwhile, the precursor research, the Earth generating its own signals, has genuine support, but is still preliminary and plagued by false alarms, and is nowhere near being a reliable prediction tool. That is the truth. It is not as satisfying as either a confident yes or a smug no. And here, on this channel, when the space weather has been quiet, I have told you that quiet, that the conditions for any solar seismic link were absent, that the framework had nothing to bite on. This time is different, because this time the conditions are not quiet. This time a real storm is arriving into a planet that is, right now, unusually loud underfoot. So let us go look at what the Earth has actually been doing while this storm has been on its way. While that cloud of plasma has been crossing the gulf between the sun and us, the planet it is heading for has been putting on a show of its own, and the geography of it is what makes you stop and look twice. This is not one region acting up. It is a scattering of activity across the entire Pacific, on opposite sides of the world, in the days bracketing the storm's arrival. Let me walk you through it, because the pattern is real, even if its meaning is the open question. Start in the far North Pacific, on the Kamchatka Peninsula in the Russian Far East. There is a volcano there, called Sheveluk, one of the most active in the world, and it has been heightened ever since the enormous Kamchatka megaquake of July 2025 rearranged the stresses in that entire region. In the last few days, it has been blasting ash columns to around 8,000 meters above sea level. 8,000 meters. That is roughly the cruising altitude of a jetliner, a wall of ash punched straight up into the flight levels. And Sheveluk has been getting more active, not less. Now jump south to Indonesia, on the far side of the Pacific, where a volcano in the Lewotolak and Lewatobi complex has been sending up ash columns past 4,000 meters. And here's a rule of thumb worth knowing. When a volcano starts putting ash to 4,000 or 5,000 meters, around 15,000 feet, you are no longer looking at routine grumbling. You are looking at a serious explosive eruption. So we have notable explosive activity in the Russian far north, and notable explosive activity in Indonesia thousands of miles apart at the same time. Then there is the one I have told you about before, the one we did a full deep dive on, the submarine eruption at Titan Ridge in the central Bismarck Sea near Papua New Guinea. If you have been with me, you know the story. It started in early May, and instead of fading, it has kept going week after week, and it has very likely become the single largest volcanic eruption anywhere on Earth so far this year. Satellite imagery from June 4th shows it still going, the sea stained with discolored water, pumice rafting up from a vent on the seafloor, steam venting at the surface. An underwater volcano, weeks into an eruption that has not stopped. and then Hawaii, where Kilauea has been doing something genuinely remarkable. Its current eruption has been running in episodes, pulses of lava fountaining from the summit, and it has just set a record by reaching its 48th fountaining episode. 48 separate bursts in one eruptive sequence. That is not a sleepy volcano. That is a volcano in an unusually energetic, rhythmic, sustained phase. And there is something almost hypnotic about that rhythm, because episodic fountaining like this is the volcano pressurizing, releasing, and repressurizing on a clock of its own. A deep magmatic pulse beating again and again. It is the kind of behavior that makes you want to ask whether anything outside the volcano could be setting the tempo, even as you remind yourself that Kilauea has kept its own time for as long as humans have watched it. It does not stop there either. The wider monitoring picture this week reads like a roll call of the Ring of Fire. In the Philippines, Mayon and Canlaon have stayed active. In Ecuador, Sangay has been logging hundreds of explosions a day, and Reventador has kept erupting at a high level. Across Indonesia, Semeru, Ibu, Dukono, and Merapi have all continued their daily eruptive routines. In Alaska, Great Sitkin sits at a watch level with a slowly oozing lava flow, while Sheshalden and Kuprianov carry advisories. In Italy, the restless caldera of Campi Flegrei has been in the news for its ground deformation. In Guatemala, Fuego has thrown out its periodic explosions. None of these, on its own, is extraordinary. Every one of them is a volcano doing roughly what that volcano does. But laid end to end, in a single week, alongside a strong solar storm bearing down on the planet, the list has a certain weight to it. Now, turn from the volcanoes to the faults, because they have been just as busy. Off the northern Kuril Islands, in that same Kamchatka Kuril subduction zone, a cluster of earthquakes broke out as the storm approached. A magnitude 6.1, a separate magnitude 6.0, a pair of magnitude 5.5s. At least 4 substantial quakes in a single day, in one of the most dangerous trenches on the planet, the kind of shallow offshore subduction setting that can, when it wants to, generate the very largest earthquakes we know of. And on the opposite side of the world, in Greece, on the island of Evia, a shallow swarm let go almost simultaneously. A magnitude 5.5, a 5.2, and a 4.9, 3 of them inside about 5 minutes. So lay it all out on a map. Kamchatka erupting, Indonesia erupting, the Bismarck Sea erupting, Hawaii fountaining at a record pace, the Kurils shaking with a sequence of strong quakes, Greece swarming, all of it clustered around the arrival of a strong geomagnetic storm. I would be lying to you if I said that doesn't make the hair on the back of your neck stand up a little. It is exactly the kind of convergence that makes a person want to draw a line connecting all the dots. But here is where I have to be the honest guide, not the salesman, because this is the whole reason the question is so hard. The Earth is always doing this. On any given week of any given year, there is significant volcanic and seismic activity happening somewhere. The planet averages 2 to 3 earthquakes of magnitude 5 or larger every single day. Over the past week, there were 94 quakes of magnitude 4.5 or greater worldwide, and that is a completely normal background rate. There are always a dozen volcanoes erupting somewhere on Earth at this very moment. So when you go looking for activity to line up with a storm, you will always find some, because there is always some to find. The human brain is a pattern detecting machine, and it does not switch off just because the pattern might be a coincidence. The convergence is real. Whether it means anything is precisely the thing the energy budget and the weak correlations leave unresolved. And tomorrow, when the storm actually hits this already restless planet, is in a strange way another data point in an experiment that has been running, unsolved, for 50 years. But before we get to tomorrow, there are 2 more pieces of this puzzle I have to show you, because they are the most specific and the most disputed of all. There is one observation buried in all of this that is more specific than the rest, and it deserves a careful look because it sits right at the heart of everything we have been talking about. It comes out of Tomsk in Siberia, where a monitoring system measures something called the Schumann resonances. And in the last couple of days, that system reportedly picked up an anomaly. Let me tell you what Schumann resonances actually are first, because the name sounds exotic, and the reality is beautifully simple. The space between the surface of the Earth and the ionosphere, that electrified ceiling about 60 miles up, forms a closed cavity. A gap between two conducting shells, wrapped all the way around the planet. And just like the air inside a guitar body has natural notes it likes to ring at, this planet-sized cavity has natural electromagnetic frequencies it likes to resonate at. The fundamental note is about 7.83 Hertz, with overtones climbing up at roughly 14, 20, 26, 33 Hertz, and so on. What keeps these notes ringing is lightning. Every lightning strike on Earth, and there are millions every day, plucks the cavity like a string. So the Schumann resonances are, in a very real sense, the heartbeat of the planet's electrical system, a constant hum set by the world's thunderstorms. They are completely real, and they are measured continuously. The anomaly reported from Tomsk was a roughly 15-minute window in which the signal, right around 24 Hertz, ran stronger than normal. And the claim attached to it is that the 20 to 30 Hertz band is a known range for pre-earthquake signals, that this kind of disturbance in the cavity can show up before a large quake, and that Tomsk is a particularly good place to catch it because it is high latitude, far from the electrical noise of big cities and power grids. Now, how seriously should you take that? Here is the careful answer. The underlying idea is connected to that better supported precursor research we talked about. The notion that a stressed region of crust can change the conductivity of the ionosphere above it and subtly alter how the cavity rings. That is a real area of study, but the research linking specific Schumann anomalies to specific earthquakes is preliminary, contested, and riddled with false alarms. A single 15-minute blip at one station, by the honest admission of anyone looking at it, is just an anomaly. It is not picked up everywhere. There is no guarantee it precedes anything at all. Spectrograms are full of wiggles, and telling a meaningful signal from random noise is genuinely hard. So file this one exactly where it belongs. A real measurement technique, watching a real planetary phenomenon that produced an interesting blip, which may mean something, and very probably means nothing. It is a thread worth watching, not a prediction worth fearing. And it connects straight back to our central question, because it is the electrical coupling between the ground and the sky, the very link this whole video is about, caught flickering at a single station in Siberia. There is a second specific piece, and this one is about the west coast of the United States, and it is a more sophisticated idea than the simple solar trigger, so I want to give it its due. It also comes with a warning label, because some of the specific earthquakes attached to it could not be confirmed in the official catalogs at the time I'm putting this together. So treat the individual numbers as reported rather than verified. But the underlying geophysical concept is real and worth understanding. The concept is about something called tremor and synchronization. On a great subduction zone like Cascadia, the offshore fault that runs from Northern California up to British Columbia, there is a constant, low-level seismic murmur happening deep underground. Not earthquakes you can feel. A faint, continuous tectonic tremor produced as the deep parts of the fault slowly slip. And researchers have found that this tremor tends to synchronize across the different segments of the fault, the different blocks all humming more or less together. The unsettling part of the hypothesis is this. The more synchronized a subduction zone is, the more primed it may be to rupture all at once, in a single catastrophic go, rather than in smaller piecemeal failures. The argument in the source material is that a large enough earthquake near the trench can desynchronize that tremor, knock the blocks out of step with each other, and that this anti-correlation between big nearby quakes and the background tremor has been most clearly identified for Japan, with relevance to Cascadia. It ties this to a reported magnitude 5.7 inside the Juan de Fuca plate near Cascadia, along with reported activity on the Garlock Fault in Southern California and a string of swarms across Nevada, painting a picture of the western United States as a stressed landscape that is shifting, and, in the source's words, unlocking. Here is my honest read. Episodic tremor and slip on Cascadia is absolutely real and intensely studied, and the relationship between that deep tremor, slow slip, and the timing of the next great megathrust earthquake is a live frontier of seismology. The last time Cascadia let go was an estimated magnitude 9 in the year 1700, and it will go again. That is geological certainty. But the specific claim that one moderate quake meaningfully changes the rupture odds is a hypothesis, not a settled fact. And the idea that the Garlock or the San Andreas could rupture at any time is true only in the trivial sense that they are always loaded and we never know the day. What I will say is this. Notice the direction of this explanation. It is entirely about the Earth's own internal machinery. Plates, stress, tremor, faults talking to faults. No sun required. And that is a healthy reminder. The Earth has powerful internal drivers of its own, completely independent of anything happening 93 million miles away, which makes the central question even harder. Because to prove the sun nudged a fault, you would first have to rule out everything the Earth was already doing on its own. And the Earth is always doing plenty. Let me bring you back to the storm itself, because there is something about it you deserve to understand. And it is the same something that fuels half the conspiracy theories about space weather. The honest truth is that nobody, not NOAA, not me, not anyone, can tell you tonight exactly how strong tomorrow's storm will be. And the reason why is one of the most counterintuitive facts in all of space weather. The strength of a geomagnetic storm does not depend mainly on how fast the plasma is going or how dense it is, though those matter. It depends overwhelmingly on one thing. The direction the magnetic field inside that cloud of plasma is pointing when it arrives. Specifically, whether it points north or south. This is the single most important variable, and it has a name, the BZ component. When the magnetic field in the incoming cloud points south, it locks onto Earth's own northward field, like two magnets snapping together, a process called reconnection, and it opens a door that lets the storm's energy pour straight in. When it points north, the fields repel, the door stays mostly shut, and even a fast, dense, dramatic-looking cloud can fizzle into a disappointment. And here is the maddening part. We cannot measure which way that magnetic field is pointing until the cloud is almost on top of us. We have a spacecraft parked about 1 million miles upstream, at a spot called L1, and it is our early warning sensor. But by the time the plasma reaches it and tells us the orientation, we have somewhere between 15 and 30 minutes before that same plasma hits Earth. That is the entire warning. 30 minutes for an event 2 days in the making. So when NOAA issues a G3 watch, they are not giving you a guarantee. They are giving you a probability, an educated forecast of the most likely outcome, knowing full well that the deciding factor will not reveal itself until the last half hour. This is exactly why, with the first pulses of this solar activity, the storm came in weaker than the worst case some had feared. People expecting a G4 got a G2. That is not a cover-up. That is not NOAA hiding the truth. That is what an honest, probabilistic forecast looks like when the deciding variable is genuinely unknowable until the final moments. I have said this before, on this channel, and I will say it again, because it matters. The gap between the forecast and the reality is not a conspiracy. It is the speed of light and the limits of where we can put a sensor. And there is one more wrinkle in this particular storm that makes the forecast even slipperier than usual, and it is worth knowing about. This incoming cloud is not arriving into clean, undisturbed space. The sun has been firing repeatedly from the same region for over a week, and there is more than one cloud of material strung out along the path between us and the sun. When coronal mass ejections stack up like that, traveling through solar wind that an earlier eruption already plowed through, they can interact, merge, slow each other down, or speed each other up, and the magnetic fields inside them can get twisted and tangled in ways no model can fully predict. There was even a filament of solar material launched a day earlier that is set to collide with the leading clouds somewhere in the inner solar system. So the thing arriving tomorrow may not be a single clean shock at all. It may be a pileup, and the orientation of the magnetic field inside a pileup is anyone's guess until it washes over that sensor a million miles upstream. This is the real texture of space weather forecasting, and it is humbling, and it is honest, and it is nothing like the all-knowing control room people imagine when they assume every surprise must be a secret. And that brings me to the theories, because a video like this always summons them, and you deserve to have them addressed head-on rather than ignored. So let me take them seriously, one at a time, and tell you where each one stands. The first, that scientists are secretly hiding that solar storms cause earthquakes. Here is the problem with that. There is nothing to hide. The correlation studies are published in the open, in journals anyone can read. The reason the strong version of the claim is not accepted is not suppression. It is the energy budget, which we walked through. The honest gap here is not concealment. It is communication. The nuanced reality, weak correlations, an unproven trigger, real but preliminary precursor work, almost never survives the trip into a headline. That is a failure of translation, not a cover-up. The second, that NOAA downplays or downgrades these storms on purpose. We just dismantled that one. The deciding variable arrives 30 minutes before the storm. A forecast that lands wide of the worst case is the system working honestly, not lying to you. The third, and the one that comes up every single time. HARP, or some secret weather weapon, energizing the planet and setting off the volcanoes. I will give you the same answer I always give, because it is the one the physics demands. Look at the energy. The magnetic energy the sun pours into this system, and the energy locked inside a volcano or a fault, exceed anything any human transmitter on Earth can produce by something like 17 orders of magnitude. That is not a small gap you can hand-wave away. That is the difference between a firecracker and the entire output of the sun. There is no physical pathway by which a radio facility couples into a magma chamber. It is not that it is unlikely. It is that there is no mechanism, none, at the energy scale required. And the fourth, the freshest one, that a huge full halo coronal mass ejection seen launching this week is a secret Earth-directed strike they are not warning us about. This one is a simple misunderstanding of what we were looking at. That halo erupted from the far side of the sun, the side facing directly away from us. A halo appearance just means the cloud is expanding toward or away from the observer, and this one was blown out the back door, away from Earth. It is no threat to us now. The genuinely interesting fact, the one worth holding on to, is that the active region that produced it is large, and the sun's rotation will carry it around to face us over the next couple of weeks, which is its own quiet reminder that the sun, deep into the supposedly calming descending phase of its 11-year cycle, is still loaded. By raw sunspot count, this cycle has run about a quarter weaker than the big cycles of the late 20th century. Yet by the measures of its energetic, high-frequency behavior, it has kept pace with them. The sun is not done with us, which is exactly why tomorrow matters. So here we are, on the edge of it. Let me pull the whole thing together, because by now, you can see, this was never really a story about pretty lights. And it was never really a story about a cover-up either. It is a story with two layers, and both of them are true at the same time. The first layer is solid ground, and it is genuinely important on its own. A strong geomagnetic storm, a G3, arrives tomorrow, around the middle of the day, the latest pulse from a sun that has been unusually active for over a week. It hits a magnetosphere that was already rattled by a moderate storm just 3 days earlier, which means the planet is, in a sense, primed. The second punch landing before the bruise from the first has faded. The consequences we can state with confidence. Aurora pushed down into the northern United States, a real chance of seeing the northern lights far south of where they belong. Possible disruptions to high-frequency radio and to GPS precision. Induced currents flowing through the power grid that operators will be watching closely. A small chance of a radiation storm riding in on the shock. And the exact severity hanging on a magnetic orientation we will not know until 30 minutes before impact. That alone is worth your attention tomorrow night. Look north. You may see something. The second layer is the open question, the one that gives this whole thing its weight. As the storm arrives, the earth beneath it is already restless, in a way that is hard to ignore even when you know better. Volcanoes erupting from Kamchatka to Indonesia to the Bismarck Sea. Kilauea fountaining at a record clip. Earthquake sequences in the Kurils and in Greece on the same day. And a real, legitimate, decades-old scientific question hanging over all of it. Can the energy this storm pours into the ground, the induced currents, the shaking field, the perturbed global circuit, act as the faint nudge that tips an already critical fault or magma system over its edge? And the honest answer, the one I owe you, is the most interesting answer of all, because it refuses to be simple. The energy budget rules out the sun ever causing an earthquake. Full stop. The trigger idea, the gust of wind on the balanced boulder, survives, but only barely, and it remains unproven for geomagnetic storms specifically, even though we know for certain that other tiny forces, like the tides, really do nudge faults. The correlation studies are real, but weak and fought over. The precursor research, the Earth lighting up before it breaks, is the genuinely promising thread, but it points the other way, from the ground to the sky, and it is still young. And the convergence we are watching this week, all those volcanoes and quakes lining up with the storm, is exactly what you would expect from a planet that is always rumbling somewhere, viewed by a brain that cannot help connecting dots. So why, after 50 years, can science not just close the case one way or the other? That is the real mystery, and it is not the mystery the conspiracy theories think it is. It is not that someone is hiding the answer. It is that the perturbation is genuinely real and genuinely measurable. The geological systems are genuinely sensitive to tiny triggers, and yet the connection between the storms in space and the solid Earth stays maddeningly, statistically slippery. Every instrument confirms the energy arrives. No instrument has ever cleanly caught it pulling a trigger. The door is open a crack, and after half a century, nobody has walked through it, and nobody has managed to shut it either. Which is what makes tomorrow worth watching for more than the aurora. Because in a strange way, the storm arriving on June 8th is one more run of an experiment that has never given a clean result. A strong, well-measured surge of energy pouring into a planet that is already, audibly, restless beneath our feet. The magnetometers will record every tremor of the field. The seismographs will record every shudder of the ground. And somewhere in that data, if the connection is real, it will leave a fingerprint. And if it is not, it will leave nothing but the usual noise of a living planet. Either way, the instruments are watching. And so, now, are you? The storm is 2 days out and closing. Look up tomorrow night. But maybe, just maybe, pay a little attention to what is happening under your feet as well. because the sun is about to knock, and the only real question left is whether the Earth, for once, answers back.